Swayam Prabha. Digital India. Educated India.
So in this section, we will try to solve some distillation related problems. These involves flash, batch distillation as well as continuous distillations. Mostly these problems are taken from GATE questions. So the first question goes something like this. An equimolar mixture of A and B, A being more volatile, is flash distilled continuously at a feed rate of 100 kilomoles per hour, such that the liquid product contains 40 mole percent of A. If the relative volatility is 6, then the vapor product in kilomole per hour is. Okay, so that's a question. First, we will write down the data given in this problem. So the data, it is a equimolar mixture. So the feed composition is 0.5 and the feed rate is given as 100 kilomole per hour, and the liquid product contains 40 mole percent of A. So that is the residue composition is 0.4 and the relative volatility is 6, and we need to find the vapor product, which is D in kilomole per hour. Okay, and the operation is flash distillation. We can probably draw a small schematic here to represent this operation. So feed F with composition XF is continuously flashed. This is the distillate and this is the residue, and here XF is 0.5, F is 100 kilomole per hour, here XW is 0.4, and we need to find D. Now in flash, we know that the composition of the outgoing streams are in equilibrium, and we know that the relative volatility is constant, which is given as 6. Using this, we can find the composition at the distillate, that is YD. What we do is we say that the definition of alpha is y by 1 minus y over x by 1 minus x, and we can rewrite this as y is equal to alpha x by 1 plus alpha minus 1 times x. Sorry, this is x, and then we can write this for yd and xw. So in this equation, we know xw, we also know alpha. Let's substitute that. So alpha is 6 times xw is 0.4, 1 plus alpha minus 1 is 5 times 0.4. So if you solve, you will get yd is 0.8. So this is 0.8. So now what we can do an overall material balance. So F is equal to W plus D, and we know that F is 100, W and D we do not know, we will keep it like this. So this is equation 1, and then we can do a species A balance. So F is 100, XF is 0.5, W we do not know, but XW is given as 0.4, D we do not know, but YD we found as 0.8. So we have 50 is equal to 0.4 W plus 0.8 D. Since we want to find D, we can replace W from equation 1, because we can write W is equal to 100 minus D. This is from equation 1. So, substituting that in equation 2, we have 50 is equal to 0.4 times 100 minus D plus 0.8 D. So, we get 40 minus 0.4 D plus 0.8 D. So, this is basically 0.4 D is equal to 10. And this becomes 25 kilomoles per hour. Okay. So, what we have done in this problem is that it is a flash distillation, and since one of the product composition XW is given, and we know in flash distillation this XW should be in equilibrium with YD. That is the important concept in flash distillation, and we use the relative volatility, which is constant, to relate the vapor phase composition Y and the liquid phase composition XW, and based on that we obtain the composition of the vapor as 0.8, and then using a material balance, overall material balance and the species material balance, we have 2 equations and 2 unknowns, and from here we can eliminate W and get the distillate, the product, as 25 kilomole per hour. This problem is related to batch distillation. So, here distillation of a non-reactive binary mixture with components A and B is carried out in a batch still, as shown in the figure below. The initial charge of the mixture in the still is 1 kilomole. The initial and final amounts of A in the still are 0.1 kilomole and 0.01 kilomole respectively. Use a constant relative volatility of 4.5, and the mole fraction of B remaining in the vessel is. So, we need to find what is the mole fraction of B in the residue. Again, we will first write down the information available in this problem. So, we have F is equal to 1 kilomole, and it said initial amount of A in the still. So, that is F times XF is given as 0.1 kilomole, and the final amount of A in the still, so that would be W times XW is also given as 0.01 kilomole, and alpha is given as 4.5, and we need to find the mole fraction of B in the residue. So, that is nothing but 1 minus XW. Okay. So, this is what we want to find out. So, this is a operation is a batch distillation. Operation is batch distillation with constant relative volatility. That means we should be able to use the integrated Rayleigh's equation for this problem. We can also note that from here, since we know F times XF is equal to 0.1 and F is 1, we can find that XF, that is the feed composition, is 0.1. Okay. So, this is something we can easily infer. And now, let us write the Rayleigh's equation. So, this is ln of F by W is equal to 1 by alpha minus 1 So, this is Rayleigh's equation, and since we are given the values of Fxf and Wxw, what we could do is we can rewrite this equation a little bit differently. So, let us multiply this equation with multiply this equation with alpha minus 1. So, you have alpha minus 1 times ln of f by w is equal to ln of xf times 1 minus xw over xw into 1 minus xf we will get ln of fxf by wxw is equal to alpha ln f times 1 minus xf by w times 1 minus xw. So, this is also Rayleigh's equation, but in slightly in a different form. And the reason why we wrote this way is that we know this fxf and wxw in the problem, it is given. So, f times xf is 0.1 and w times xw is 0.01. So, this gives ln of 10 and that is equal to alpha, which is 4.5 times ln of f is 1 and 1 minus xf is 0.9 and we do not know w, and w times xw is 0.01. So, we have ln of 10 is equal to 4.5 times ln of 0.9 over w by w minus 0.01. So, from here we can solve w, this comes out to be 0.55. So, w is 0.55, but we already know that w times xw is 0.01. So, from here we can solve for w xw. And we get 0.0182, and what we need is the composition of component B in the residue, that is 1 minus xw. So, that is 0.982. So, this is the answer. So, in this problem what we have done is this is a direct application of Rayleigh's equation, but the kind of information given in the problem requires us to rewrite the Rayleigh's equation in a different form or equivalent form, and from here onwards it is a direct substitution of the knowns, and the only unknown in this problem is the residue amount w. Okay. Once we obtain w, we can use this given data w times xw is 0.01, and from here we can solve for xw, and that is 0.982. So, in this problem the vapor liquid equilibrium curve for a binary mixture AB may be approximated by a linear equation over a narrow range of liquid mole fractions as follows. So, that is, we are given with an equilibrium line equation following a straight line formula. So, here Ya star is the mole fraction of A in the vapor. 100 moles of feed with a composition of 20% mole percent is batch distilled to a final residue of 0.2 using the Rayleigh's equation. The number of moles of the residue left behind in the distillation unit up to 2 digits after the decimal point is to be obtained. So, again the data given is that first of all the equilibrium line is given 1.325 x plus 0.121 and this is only valid in the range 0.2 to 0.3, and F is 100 moles. The feed XF is 0.28 and XW is 0.2, and we need to find W. So this is a direct application of Rayleigh's equation. So we write the Rayleigh's equation for batch distillation, which is ln of F by W is integral from XW to XF dx by y star minus x. So in this equation, y star is given in terms of linear relations. So we can find y star minus x as 1.325 x plus 0.12 plus 0.121 minus x. So we will get 0.325 x plus 0.121. Okay, so now we are going to integrate this dx by y star minus x in the limit of 0.2 to 0.28. So here we will use the formula that dx by ax plus b will be 1 by a ln of ax plus b. Okay, so this is the integral formula for the integration. So using this formula, we will get in the limit of 0.2 to 0.28. So now substituting this limit, we will be able to get this integral this becomes 0.4025, and this is nothing but ln of F by W. And we know that in this problem F is 100 moles, W is something that we want to find out, and this is equal to 4025, and from here you can solve for W. I will get 66.86 moles. Yeah, so this is basically a batch distillation problem where we start with the Rayleigh's equation, and the equilibrium line is given using this particular relationship, and then we know the limits xw and xf, and it's a direct integration substitution, and then we will know that the only unknown, that is W, as 66.86 moles in this problem. So in this problem, 100 moles of a binary mixture containing 60% of A and 40% of B is treated in a batch distillation still. After 1 hour, 70 moles of the distillate is collected, leaving behind the residue W. The relative volatility is 2. The average mole fraction of A in the distillate is to be obtained. So first we will write the data given. So F is 100 moles, XF is 0.6, and at the end of the distillation process, D is given as 70 moles, and relative volatility is 2, and we need to find YD average. Okay, this is a unknown quantity. So since it's a batch, so operation is batch distillation with constant alpha. So, we can use Rayleigh's equation, the integrated form, which is ln of F by W So, in this equation F is known, W is unknown, but W is something we can obtain from the overall mole balance, which is F minus D. Since we know both F and D, F is 100, D is 70. So, that is W is 30 moles, we know this. So, the left hand side is knowable, and on the right hand side alpha is known, XF is known, but we do not know XW. So, that is one unknown in this problem. So, let us write down all the things that we know. So, we say ln of 100 by 30 for F by W, and alpha is 2. So, alpha minus 1 is 1. So, the prefactor is just 1, and then we have ln of XW is 0.6, 1 minus XW, and here 1 minus XF is 0.4 times XW plus ln of 0.1 minus XW by 0.4. So, now everything is actually in logarithm. So, we will write as the following: 0.6 times 1 minus XW times 1 minus XW. Here we have 0.16 XW. So, if you rewrite this, we will get a quadratic equation. You get a quadratic equation for XW, and then you can solve this, and we will get XW is 0.402. You will get two solution. Other solution will have more than 1, which is not permissible because it is a mole fraction. So, we take the lower value, which is 0.402. The question that we need to ask is YD average. For this, we will do an overall material balance, overall species balance actually, species balance. So, F times XF should be equal to D times YD average plus W times XW. So, F is 100 moles, XF is 0.6, D is 70 moles, YD we do not know, and W is 30 moles, and XW is something we found as 0.402. So, from here we can solve for YD average, and this would be about 0.686. So, in this problem 100 moles of acetonitrile and nitromethane, we will consider this as A and this is B, is differentially distilled in a batch distill at a pressure of 70 kilopascal. The feed contains 74 mole percent of acetonitrile. Distillation is continued till the liquid left behind in the still contains 32 mole percent of acetonitrile. The vapor liquid equilibria for the system at this pressure are correlated as follows. So, the equilibrium line is given in terms of linear equations over a range of compositions, where x and y star refers to the mole fraction of acetonitrile in the liquid and the equilibrium vapor respectively. Find the average composition of the distillate collected. So, we will write the data given first. So, F is 100 moles and the feed composition is 0.74 and XW is 0.32 and we have the equilibrium line Y star is 1.05x plus 0.13. This is for composition from 0.3 to 0.52 and another equation for composition in the range of 0.52 to 0.8. And we are asked to find the average distillate composition. So, the operation is the batch distillation. So, we will start with the Rayleigh's equation. So, here XW is 0.32 and XF is 0.74, but this can be decomposed into two limits 0.52 to 0.32 to 0.52 and then from 0.52 to 0.74. And the reason why we split this integral into two parts is that in this range from 0.32 to 0.52 we can use this equilibrium relationship, and for the other limit from 0.52 to 0.74 we can use the other equilibrium. So, that is the reason why we are split into two parts. And so, now we will find this integrals. So, here y star minus x, to get this y star minus x we will use this relationship. So, y star minus x is 0.05x plus 0.13 and integral of this will give you 1.325 and the next integral, that is from 0.52 to 0.74 dx by y star minus x. So, we will take this, we will get minus 0.23x plus 0.28 and this integral will give you something like 1.648. So, we can add these two integral now. So, we get ln of f by w is equal to 1.325 plus 1.648 and f is 100 moles, it is given already. So, from here we can solve for w and this would be about 5.115 moles. Since f is known and w is known, we can find d as f minus w and this is about 94.885 moles. So, now we know all the products and the feed and the only unknown composition is YD. So, we write species balance F times XF is D times YD average plus W times XW. So, F is 100 moles, XF is 0.74 and D is 94.885, YD is unknown, W is 5.115 moles and XW is 0.332. And then solving this, you will get YD average as 0.762. So, in this problem, a distillation column handling a binary mixture of A and B is operating at total reflux. So, this is the continuous rectification or fractionating column operating under total reflux. It has two ideal stages including the reboiler. The mole fraction of the more volatile component in the residue is 0.1. The average relative volatility alpha is 4. The mole fraction of A in the distillate is to be found. So, let us write down the data given. So, this is total reflux. So, R is infinite and n plus 1 is given as 2. So, the number of stages including the reboiler is 2. So, basically, so the reboiler itself is a stage. So, actually there is only one single plate, one plate and then one reboiler, together it is two ideal stages, and the mole fraction in the residue XW is 0.1 and alpha is 4, and we need to find what is in the distillate, that is XD, this to be found. And as we mentioned in the class, for continuous distillation with constant alpha and total reflux, we can use Fenski's equation for calculating the number of theoretical stages, and the Fenski's equation is given as n plus 1 is equal to ln of xt by 1 minus xt times xw by 1 minus xw. So the Fenski equation is given as xt by 1 minus xt times 1 minus xw by xw by ln of alpha. So basically this problem is a direct substitution, because we know that n plus 1, that is 2, xt is something that we want to find out, but xw is given. So this is 1 minus xw is 0.9, xw is 0.1, and we have ln of alpha is 4. So basically we get 2 times ln of 4 is equal to ln of 9 times xt by 1 minus xt. So this is nothing but 16 is equal to 9 times xt by 1 minus xt, and then if you solve for xt from here, you get 0.64. Okay, this is the answer. So this problem is a direct application of Fenski's equation, which is relevant for calculating the number of theoretical stages under total reflux and constant relative volatility, and all the unknowns are all the variables are known except xt in this equation. So it's a direct substitution and obtaining xt from here. So in this problem, consider the equilibrium data for methanol water system at 1 bar given in the figure below, and a distillation column operating at 1 bar is required to produce 92% of methanol. The feed is a saturated liquid. It is an equimolar mixture of methanol and water. The minimum reflux ratio is. So in this problem, we are given with the equilibrium line, and so let's write down the known data. So what is known for us is that distillate composition is 0.92, feed is a saturated liquid, and the feed composition ZF is 0.5 because it is a equimolar, and we need to find the minimum reflux ratio. That is a question. And what we need to do first is to find out the Q line, and the Q line will intersect the 45-degree line at ZF. So that is here. So this corresponds to ZF of 0.5, and then it is said to be a saturated liquid. For saturated liquid, the Q line is a vertical line. So, this is Q line here, okay, and XD is 0.92. So, 0.92 can be marked somewhere here. This is 0.92. For minimum reflux ratio, we need to draw the enriching section operating line starting from XD on the 45-degree line and then intersect the point connecting the point where the Q line and the equilibrium line meets each other. So, to obtain the minimum reflux ratio starting from XD, we extend the line such that it touches the intersecting point between the Q line and the equilibrium line, and then find the corresponding intercept. So, we are somewhere here, and we know that this intercept, the intercept that we see here is nothing but XT by R minimum plus 1, and we read this value to be something close to 0.61. So, from here R minimum plus 1 is equal to XD by 0.61, XD is 0.92, and from here if you solve for R minimum, you get something close to 0.508. So, this is an important problem because it allows us to find out the minimum reflux ratio from the enriching operating line. So, the way we did this was to find the XD on the 45-degree line, and then we identified the Q line because the feed is saturated liquid. For saturated liquid, the Q line is a vertical line from XF to the equilibrium line. So, we identify the point of intersection at 0.5 and 0.78, and then we connect these two line, and then we find the intercept on the y axis, and we know that the intercept is related to the minimum reflux ratio, and from here we can get this. In this problem, another point is given here just to confuse, because sometimes a student may consider the Q line is a horizontal line which is only true for saturated vapor. So, this point is given to confuse, and this line is only applicable for saturated vapor, but here the feed is a saturated liquid. So, we should draw this line, and if a student incorrectly thinks that this is the line corresponding to the saturated liquid, one would draw the optimal line through this point and get an incorrect value. Okay, so this point is given just to trick the student. So, in this problem, a binary distillation column is designed by the McCabe-Thiele method to get the distillate mole fraction of 0.9. The enriching section operating line has an intercept with the y-axis at 0.3 mole fraction. We need to find the ratio of liquid to vapor molar flow rate in the enriching section. So, again data given, XD is 0.9 and the operating line intersecting the y-axis is XD by R plus 1 is given as 0.3, and we need to find the L by G ratio. This is unknown. So, from this data given, we can solve for R. R plus 1 is 0.9 by 0.3. So, R is equal to 2. So, reflux ratio in this problem is 2, and we also know that L by G is nothing but R by R plus 1. So, this is 2 by 3, okay, that is 0.667. So, the answer is 0.667. So, in this problem, a binary feed consisting of 25 mole% liquid and 75 mole% vapor is separated in a staged distillation column. The mole fraction of the more volatile component in the distillate product is 0.95. The molar flow rate of distillate is 50% of the feed flow rate, and the McCabe-Thiele method can be used to analyze the column. The Q line intersects the operating line of the enriching section at 0.35 and 0.5 on the XY diagram. The slope of the stripping section operating line is to be found. So, first we will write down the known data. XD is 0.95 and the distillate D is 0.5 times F. The feed is said to have 25 mole% of liquid and 75 mole% of vapor. So, we will take a basis of F is equal to some 100 moles. In this 25 moles are liquids and 75 moles is vapor. So, what this means is that when we introduce the feed, it will increase the feed flow rate to the extent of 25 moles and then the vapor flow rate to the extent of 75 moles. So, this can be written as L bar minus L, this is equal to 25 moles, and G minus G bar is 75 moles. And what we need to find is the slope of the stripping section, which is nothing but L bar by L bar minus W. Okay. So, this is what we need to find. And another useful information that is given in this problem is that the Q line intersect the operating line of the enriching section at 0.35 and 0.5. So, what that means is, let us draw a schematic. So, this is the 45-degree line and this is the equilibrium line, and so the enriching operating line starts at 0.95 and then this touches the, so let us say that the Q line is somewhere here, we do not know exactly, but we know that this enriching line and the Q line is touching at this point, and this point is noted as 0.5 here and 0.35 here. So, since we know that the enriching line and the Q line is intersecting at this particular 0.35 and 0.5 and the another point is at 0.95 and 0.5, we can find out the slope of this enriching line, and this slope of enriching line is given by R by R plus 1 and this is also equal to L by G, and this is nothing but the slope of this line. The slope of this line is 0.95 minus 0.5 divided by 0.95 minus 0.35 and you get something like 0.75. So, from here if you solve, you will get R equal to 3. So, the reflux ratio can be obtained from this data. Once we know R, we can also find L, that is nothing but R times D, and R is 3, D is 50% of the feed and feed is taken as 100 moles as basis. So, all this will give you about 150 moles. This is L, and we already know that L bar minus L is given as 25, and from here we can solve for L bar, that is 175 moles. and the stripping line slope is given by L bar over L bar minus W, but we need to know what is W. So, to find a W, we will do overall mole balance, where F should be equal to D plus W. We have taken F as 100 moles basis, D is 50, so W also will be 50. So, the stripping line slope is then L bar over L bar minus W will be 175 over 175 minus 50. So, that is 175 by 125, and this is about 1.4. So, slope is equal to 1.4, that is the answer.